Hello students, hope you are fine. Now in this class I am going to start the quantum mechanics part 2, which you may have already read some portion of it in chemistry in the previous semester, which basically has the Schrodinger equation, its solution, how the Schrodinger equation is formed with different operators, the wave function itself. Now for that, let me share the note first. So as discussed in the previous classes, so every moving particle has a wave associated with them. Now these waves will not be any ordinary waves. These will have some specialty. These waves will be basically very complex waves because they are formed by superposition of a large number of waves having different frequencies within a certain frequency range. This complex wave is known as the wave function and it is denoted actually by psi. So here the wave function is denoted by psi, which is a position of r and t, where r is the position vector and t is the time. So the wave function will be function of both position and time. So it gives us the space-time behavior of the particle. That is, we can derive any information about the particle if we know its wave function. It has no direct physical significance, but various operators, they operate on this wave function psi and they give us information about different variables, which are the measurable quantities like velocity, position, energy, momentum, etc. We can get all the values of these observables by operating different operators on the wave function psi. So directly it is nothing, but indirectly it has all the information about the particle. First comes the probability density. The probability density is of finding out a particle at a position r and time t is denoted by mod psi whole square. So if you do mod square means psi star psi. If you do the modulus, if you do the mod square of any complex quantity, it will be the complex quantity multiplied by the complex conjugate, which is why psi star psi. So psi star psi gives you the probability density of finding the particle at a position of r and time t. The probability of finding out the particle at a position within the range dr is given by mod psi square into dr, or mod psi square into d tau in 3 dimension, where d tau gives you the elementary volume. So mod psi square d tau gives you the probability of finding the particle at the position r in time t within the volume element d tau. And what happens if you integrate over it over the whole space? So it gives you the probability of finding the particle anywhere in space. The total probability, it will obviously be 1, because I know the particle is there. I don't know the exact position, but it is there. I am confirmed. So the probability of finding the particle anywhere in space, which is the total probability, it is given by 1. So if you integrate the probability density over the whole space, you will get 1. So any wave function, this is a property for any wave function. The mod square of the wave function, if you integrate it over the whole space, you have to get 1. So by the wave function psi, we get nothing, but by the mod square, we get the probability. Now let us see what else we can get. So as I said, the probability, this equation, the equation number 1, it is called the normalization condition. That means the probability of finding the particle anywhere in space. So obviously probability has to be 1, maximum it can be 1, it cannot be greater than 1. So this is for 3 dimension, and for 1 dimension the equation reduces to this. So integration minus infinity to plus infinity psi function of xt. Look here, it was function of r in 3 dimension. In 1D it is function of x. So mod psi xt whole square into dx is 1 for 1 dimension. Now, what are the properties of wave function? Now, as psi gives information regarding the space-time behavior of a moving particle, psi has to be continuous, finite, single-valued in each point in space. This one is very important. The wave function has to be continuous, because if a wave function is not continuous or it is discontinuous at some position, suppose here, so let us take this one as a boundary. Here the wave function is like this. Beyond this the wave function drops to 0. So what is meant by this? If it has a finite wave function here, so it will have a finite probability of finding the particle here. Beyond this point the probability drops down to 0. So that cannot be possible. So probability cannot be discontinuous. As a result, psi will also has to be continuous, finite. It cannot be infinite also, and single valued, because if it is not single valued, we will have different probabilities at the same point in space, which is absurd. So psi has to be continuous, as well as the partial derivatives del psi del x, del psi del y, del psi del z, they also have to be continuous, finite, and single valued. The square of the wave function gives the measure of the probability of finding the particle at a particular position, as I said already. The magnitude of psi is large where the probability of finding the particle is high, or vice versa is more true, I think. Where the magnitude of psi is high, the probability of finding the particle there will also be high. So these are the properties of wave function. So those waves or those wave equations which follow all these properties, they only can act as wave function, or they only can represent matter in wave form. Now we come to operators. So before going to quantum mechanical operators, let us see what operators are. So an operator is a mathematical rule that acting on a function gives you another function. For example, let us take an operator O. O cap. Here the cap denotes the operator sign. So O cap is equal to d dx. Let us take O cap equals to d dx. And O cap acts on a function fx given by x square plus 2x. So if O cap, which is d dx, acts on fx, we get f prime x, which is 2x plus 2. So f prime x is another function. So O cap fx gives you another function 2x plus 2. Similarly, if a function acting on a function gives you the function back multiplied by some constant, the function is called the eigenfunction of that operator, and that particular constant is known as the eigenvalue of that operator. For example, I will give you the example. Okay, I tell you the example. Look at here. Look here. O cap acting on fx equals to alpha into fx. If we find out some function like this, then that function will be the eigenfunction of O cap, and the eigenvalue will be alpha. For example, if you do d dx of e to the power ax, what will you have? D dx of e to the power ax. It will be a into e to the power ax. So we are operating d dx on the function e to the power x, and we are getting a, the constant, multiplied by the function e to the power ax itself. So in this case, e to the power ax will be an eigenfunction of d dx with the eigenvalue a. Now, in quantum mechanics, each dynamical variable can be represented by, or it is represented by, an operator. For example, position, momentum, energy, all are represented by some operators, mathematical operators. So here is a list of those observables and operators. For example, let us take the position observable. So the operator is given by r cap. Here the cap does not denote unit vector. Remember, here the cap is operator. So r operator is r vector or just x, y, or z if you talk in terms of the coordinates. The momentum vector is given by minus I h cut grad. Grad you remember from the vector gradient divergence curve. So that gradient. In 1D it is I h cut del del x. The kinetic energy is given by minus h cut square by 2m Laplacian. Laplacian is del dot del 2x del x2 plus del 2y del y2 plus del 2 del 2 del z2. The potential energy simply is multiplied by V into R. Total energy is given by E equals to IH ka del T. So from where we are getting these operators, we will do in details in the later sections. So before that, first know the fundamental postulates of quantum mechanics. So you have to remember all the fundamental postulates, which states that there is a wave function associated with every moving particle, psi rt, which completely describes the space-time behavior of the particle in consistence with the uncertainty principle. The dynamical variables are represented by mathematical operators. For a dynamical variable alpha, the possible results of measurements are given by the eigenvalues of the operator alpha cap satisfying the equation alpha cap acting on the function psi n gives you alpha n into psi n, where this psi n is the eigenfunction of the operator alpha cap belonging to the eigenvalue an. So this is an, not alpha n. So the eigenfunctions psi n are single valued and square integrable. They form complete set of orthogonal wave functions. Next comes the probability of finding a particle in the volume element dV is given by probability P into dV, which is psi star psi dV, and the probability of finding the particle in entire space is given by integration over all space psi star psi dV is equal to 1, which is the normalization condition. So what are the, and we have one more postulates, which is the expectation value. So you have to remember the all 5 postulates. What are they? First, the wave function psi, which gives you the, or which describes the space-time behavior of the particle in consistence with the uncertainty principle. Next, the dynamical variables are nothing but operators. The third one, for every dynamical variable alpha, there are possible results of measurements which are the different eigenvalues, and different eigenvalues will have different eigenvectors for one dynamical variable. So for one dynamical variables, we have a set of orthogonal eigenfunctions. They form a complete set. The fourth one is the normalization condition, which is probability of finding the particle in the entire space is given by integration all space psi star psi dV is 1. And the fifth one is the expectation value. Expectation value is nothing but the average of the results of a large number of variables or large number of measurements for a dynamical variables, and it is given by alpha in the brackets, in the angle brackets. So this is the expectation value of the operator alpha. So alpha in the angle bracket is given by integration psi star alpha cap psi dv over integration over all space divided by integration over all space psi star psi dv. So what happens in quantum mechanics when you go on, when you measure some dynamical variable? For example, you are measuring the momentum of the particle with some mathematical operator here. So when you are measuring the momentum, you will get one value for one measurement. You do it again, you will get some other value. And if you go on repeating the measurement process, so you will get a large number of different values. The expectation value will give you the average of the results for a large number of measurements of a dynamical variable of the momentum. So mathematically it is given by psi star alpha psi dv divided by integration psi star psi dv. Now if the wave function is normalized, the denominator will be 1. So if psi is normalized here, it will be 1. So we will only have integration psi star alpha psi dv. So these are the 5 postulates or basic postulates of quantum mechanics. Now we move on to time dependent Schrodinger equations. Now Schrodinger equation is one of the fundamental equations of quantum mechanics. So it is basically nothing but an energy equation, and we are going to first know the operators and then we will form the time dependent Schrodinger equation. Now from second postulate, each dynamical variable is associated with some operator. So let us check what the operators are. So for that, let us consider a particle of mass m moving freely along the x-axis. So a free particle is moving along the x-axis with a fixed momentum px, and total energy E is equal to px by 2m. As no force is acting on the particle, it is moving in a constant potential. For our, so it will be easier for us if we assume the potential to be 0. So the potential is 0, the particle is freely moving, the energy is given by E equals to p square by 2m. Now in the operator form, the total energy operator or the Hamiltonian operator, we call the total energy operator to be Hamiltonian, which is nothing but the sum of kinetic energy operator plus potential energy operator. Here we have already taken the potential energy to be 0 as the particle is moving freely. So Hamiltonian will only be the kinetic energy operator, which is px square by 2m. So for a free particle, the wave function is a plane wave, because free particle can be anywhere in space and it can be represented by a simple wave, which is psi equals to a e to the power I kx minus omega t. Remember, this equation is correct, psi equals to a e to the power I kx minus omega t, but the second one here I missed the minus term. Okay, so if you do del psi del x, what you will get? You will get ik into a e to the power ikx minus omega t. Here my minus sign is missing, so we get ik into psi. Now px is h cut into k. As we all know, p is h by lambda, or we can write it h by 2 pi into 2 pi by lambda. H by 2 pi gives you h cut and 2 pi by lambda gives you the k, the wave propagation vector. So px is h cut into k. Now look at this thing. We have to get h cut k here. So what do we have to multiply del psi del x with? We have to multiply it with h cut by I. So h cut by I or minus I h cut into del psi del x gives you h cut k into psi, which is nothing but px, the value for momentum along x-axis. So we can write minus I h cut del del x to be the momentum operator along x-axis. So px will be denoted by minus I h cut del del x. Similarly, py will be denoted by minus I h cut del del y. Pz will be denoted by a minus I h cut del del z. So in 3 dimension, the momentum operator p cap will be given by minus I h cut common into del del x I cap plus del del y j cap plus del del z k cap, which is nothing but the gradient. That is how we get the gradient vector or minus I h cut grad to be the momentum operator. Similarly, we will find out the energy operator. So we got the momentum operator. Now, if you do the double derivative of that equation, you get del 2 psi del x2 equals to minus k square psi. So in classical mechanics, kinetic energy is given by p square by 2m. P is h cut k. So it will be h cut square k square by 2m, the total energy. So here we have to get h cut square k square by 2m multiplied by psi. So what do we have to multiply del 2 psi del x2 with? What we will multiply it? We have to multiply it with minus h cut square divided by 2m. So minus h cut square by 2m del 2 psi del x2 will give you h cut square k square by 2m into psi. So this is nothing but the kinetic energy. So the kinetic energy operator will be given by ek operator is equal to minus h cut square by 2m del 2 del x2. So we got the kinetic energy operator. Now, on the other hand, using psi equals to a to the power I kx minus omega t, we get del psi del t. If you do the derivative with respect to time, you get minus I omega psi. And if you multiply it by I h cut, then what happens? I h cut del psi del t gives you h cut omega into psi. What is h cut omega? H cut omega is nothing but the energy E. So we can write E operator to be I h cut del del t. So we got two operators, and one is total energy operator E equals to I h cut del del t. One is the kinetic energy operator minus h cut square by 2m del 2 del x2. So equating these two energy expressions, we get minus h cut square into by 2m del 2 psi del x2 is equal to I h cut del psi del t. So for a particle moving freely, this equation is true. But if the particle moves in a potential v, then what happens? What changes? On the left hand side, we will have another term v into psi. So the Hamiltonian operator will then be minus h cut square by 2m del 2 del x2 plus v function of x. So the equation becomes minus h cut square by 2m del 2 psi del x2 plus v psi equals to I h cut del psi del t. So this is the time dependent Schrodinger equation in one dimension. So what happens in 3 dimension? The del 2 del x2 will be replaced by Laplacian, and psi will be replaced by psi of rt, the psi function of position r and t. V will be replaced by v position of r and t. So the equation will look like this: minus h cut square by 2m Laplacian psi rt plus v rt into psi rt equals to I h cut del psi del t function of r and t. So this is known as time dependent Schrodinger equation. Now we got the time dependent Schrodinger equation. Next step is to derive the time independent Schrodinger equation from this time dependent one. One thing you keep in mind that we cannot derive time independent Schrodinger equation from the time dependent one always. We can do it only when the potential V is only a function of R. So this is the primary condition for derivation of time independent Schrodinger equation, that the potential V has to be function of R only. It should not be the function of T. So if V is equal to V function of R only, then we can write the Schrodinger equation like this. Okay. Now we are going to use the separation of variables and get the results. So in separation of variables, we take the function as a product of two independent functions. So we have taken psi to be product of phi and f, where phi is an independent function of R and f is an independent function of t. So psi is phi into f. Now using this equation in equation 9, we get minus h cut square by 2m ft into Laplacian phi r, because Laplacian will act only on phi, not on f, plus v into phi into f plus I cut phi into df dt, because del t was there, del t will act on f only, not on phi. So phi comes before this. Now divide the equation by phi into f and we get minus 1 by phi h cut square by 2m Laplacian phi plus v equals to 1 by f I cut df dt. Look here, the left hand side of the equation is a function of r only, whereas the right hand side of the equation, it is a function of t only. And both r and t are independent of each other. And we are getting them equal, which means that they are equal to constants. So I can write the left hand side equal to some constant and the right hand side equals to the same constant. So this is possible only when both are equal to a constant E. E will be nothing but the total energy, because you see from the dimensions. So the equation 11 reduces to minus h cut square by 2m Laplacian phi r plus v into phi r equals to E into phi function of r. And the second one, the time equation, it reduces to I cut d phi dt, sorry, df dt equals to E into ft. The equation 12, this equation is known as the time independent Schrodinger equation. Now here a solution of equation 13 is done. It is very easy. You can do the solution on your own. So we get from the solution ft equals to some constant into e to the power minus I e t by h cut. E by h cut will give you omega. So e to the power I omega t part comes from here. So the solution of the time dependent Schrodinger equation is psi rt equals to phi r into c e to the power minus I e t by h cut. Now we cannot solve equation 12, which is the time independent Schrodinger equation, right now directly, because we don't know the form of V. So we don't know anything about the potential. So dependent on different physical systems, VR will be different, and as a result the wave function phi will also be different for different V's. So for different physical systems, we can get phi r from the time independent Schrodinger equation using those various values of VR. So how will we do that? We will discuss in the next class. So for then, goodbye and be happy, stay happy and keep your family happy.